We present RAM, reachability across morphologies, a fast differentiable surrogate model that determines pose reachability without solving inverse kinematics. Every robot morphology has a unique reachable workspace. Current methods must recompute it from scratch for every new design, a process requiring millions of inverse kinematics queries. RAM breaks this limitation by learning a single representation over full SC3 poses that generalizes across morphologies, inherently accounting for self-collisions and enables reachability evaluation in nanoseconds. RAM is trained on a massive dataset of 30 billion samples across 30,000 diverse morphologies. The morphologies span 5 to 7 degrees of freedom, covering the most practically relevant designs for which analytical inverse kinematics are not always available. For each morphology, we sample poses restricted to geometrically plausible regions. Our morphologies are normalized to unit reach, which restricts reachable positions to the unit ball. Moreover, most positions inside the unit ball are also unreachable. Positions at larger radii require the robot to be nearly fully extended, leaving almost no freedom in orientation. Instead of evaluating individual poses via inverse kinematics, we approximate the workspace of each morphology by discretizing SE3 and filling the cells by sampling joint configurations, evaluating forward kinematics, and checking for self-collisions. Under the closed world assumption, any cell left unvisited is labeled as unreachable. Each pose then inherits the label of its cell, making labeling essentially instantaneous and dataset generation scalable. RAM processes each morphology as a sequence of modified Dana-Vietatenbach parameters, one token per linked joint pair. Since morphologies vary in the number of degrees of freedom, an encoder maps this sequence to a fixed-size latent vector. This latent vector conditions on an occupancy network that also receives a query pose and outputs its predicted reachability. We demonstrate RAM's utility by exploiting its differentiability to optimize robot morphologies via gradient descent. Rather than differentiating through an inverse kinematic solver via the implicit function theorem, we simply backpropagate through RAM to maximize the predicted reachability of target poses. This speeds up morphology optimization tenfold while improving the final designs compared to the inverse kinematics baseline. RAM offers a fast, differentiable reachability representation, enabling new workflows in robot design and planning that were previously too slow to be practical.